Okay, so we're going to work some problems out of section 2 just to reinforce what we talked about the other day. So the first problem we're looking at is find the first 5 terms of the sequence of partial sums. So remember the convergence or divergence of series are looking at the value of the partial sum, and if the partial sum approaches some limit L, then the series converges. So we've got this sequence which is um, basically 1 over, what is it, probably 2n plus 1 maybe? Does that make sense? Yeah, 2n plus 1. So if I wrote this out in terms of this summation notation, it'd be the summation from n equals um, 0 to infinity of 2n 1 over 2n plus 1. So when n equals 0, you get 1. When n equals 1, you get 3 in the denominator, 1/3. When n equals 2, you get 5. Anyway, the partial sums are just the sum of the terms. So the first partial sum is just 1, which is the first term. The second partial sum is 1 plus 1/3, which would be 4/3. The third partial sum would be 4/3 plus 1/5, which is, what is that, in 15ths. It's going to be multiplied by 5, so that's 20/15 plus 3/15. That's 23/15. And then the fourth partial sum is going to be 23/15 plus the next number, which is 1/7. So then you'd have a common denominator of whatever 7 times 15 is. 7 times 15. So it's 105. And so 23 times 7 is 161. And 15 times 1 is 15. So you had 161 plus 15, you get 176 over 105. And then the fifth partial sum would be 176 over 105 plus 1/9. In this case, the common denominator, can you divide 105 by 9? I don't think you can. No, but you could do 3 times that, so probably the common denominator would be 315. So you take 176 times 3, which would give you 528 over 315, and then you'd have, here we have 1/9, so that's going to be, what is 315 divided by 9? 35. So this is 35 over 315, and you add those together, 528 plus 35, you get 565 over 315. So these are the first 5 partial sums. And if this number approaches some fixed value as n goes to infinity, then this series converges. Well, now we wouldn't want to have to do that, take out a million terms. So at some point we need to know how to find the convergence of this series, whether it converges or not. We don't know how to do that yet, but that's just demonstrating what the partial sums are. First partial sum is the first term. Second partial sum is the first plus the second. Third is first plus second plus third, so forth. And since I had already calculated the first 2, I just added to the third to get the partial sums. Okay. Verify that the infinite series diverges. So we've got basically 2 rules right now. We've got the nth term test, which says that if a sub n does not go to 0 when n goes to infinity, then the series will not converge. Or this is also a geometric series with the ratio greater than 1. So this fails for 2 reasons. So you don't have to state both reasons, but this series diverges because 1, the limit of a sub n as n goes to infinity does not equal 0. And usually what we do is we state the test, which is called the nth term for test for divergence. So we'll say the series diverges because the limit of the limit as n goes to infinity of a sub n does not equal 0, which is the nth term test for divergence. And we could also too, this series is a geometric series with a equal 1 and r equal 4/3. A is the constant, so we're multiplying by 1. A equal 1 and r equals 4/3. This series is a geometric series since a equals 1 and r equals 4/3. And since r is greater than, let's look back at the test. Now, I give you a list of all the tests on a sheet of paper, so you don't have to memorize these things. You just have to find them. So it says R, the geometric series with the ratio R diverges if the absolute value of R is greater than or equal to 1. So that's the test. So I'll write that down. Since the absolute value of R is greater than 1, since R is 4/3. Okay. This series is geometric, and since this is true, the series diverges, period. Okay. We'll get used to writing this stuff out because we're going to want to verbalize what we're doing. Okay, the next one, it's not a geometric series, so the only way we can talk about divergence or convergence is using the nth term test. And again, you could say since the limit of a sub n as n goes to infinity, which is the limit as n goes to infinity of n over n plus 1 equals 1, which does not equal 0, the series diverges according to the nth term test for divergence. This is the one you always want to try first. We did try it over here, and it also worked for that one as well. Oh, by the way, I realized, so yesterday when I was recording the solution, I realized I did the first problem wrong. You probably knew that, but you said, well, he told me not to ask any questions, so I didn't ask him. By the time I got to the end, I didn't care, or I forgot. So how many people realized I did that first problem wrong? Yeah, so there was a factor of another half that I forgot to cancel the 2 out with the half. So you might go back and look at that. I also realized that when I do the recording, there's a little box that shows up here somewhere. Well, it doesn't show up right now because it's full screen, but there's a little box that tells you what I'm recording. And I was recording I was re-recording the homework solutions for Chapter 9, and I was doing it on a separate screen. And then when I recorded the stuff yesterday morning, I realized that the the screen, I captured about this much of the screen. As a consequence, I re-recorded it. That's when I realized I did it wrong, because I thought, that's not what I did this morning. I think everything else was right, but because I think I duplicated that, but I had 35 more minutes. I was like, oh, 35 minutes. Anyway. Okay, so that's those are the two tests that we know so far: the nth term test for divergence and the geometric series test. Now, it says find the sum of the convergent series. Now this is not a geometric series, and it's not. And if you look at the limit of a sub n as n goes to infinity, it will go to 0. And so actually, that's one thing we didn't talk about. So there's something called a telescoping series, which is also covered in this, should be covered in this section, but I forgot to write it down. I always remember at this point. So what you do is you can write this as n plus 1 times n minus 1. So n squared minus 1 is n minus 1 times n plus 1. And then you can use partial fractions to break up this situation. So we cross multiply, we get a times n plus 1 plus b times n minus 1. I mean n, yeah, not x, n. And we're going to let n equals -1, and we're going to let n equal +1. So when we let n equal -1, this goes to 0, and you get b times -1 minus 1. So b is equal to -1/2. And over here, you do the same thing. Let n equal 1. So you get 1 is equal to a times 1 plus 1, which if you solve for a is 1/2. So this original series becomes 1 over, or 1/2 times n minus 1 minus 1/2 n plus 1. Now let's just plot, or let's just list the values for this series as we go from n equals 2. So here we have, so what we're listing here is this. And we're not going to actually do the calculation, we're just going to leave it like this. So we have 1 over 2 times 2 minus 1 minus 1 over 2, 2 plus 1. So that's the second term. Well, it's the first term in the sequence because we're starting at n equals 2. Then you could go to the next one. That's 1 over 2 times 3 minus 1 minus 1 over 2 times 3 plus 1. And then you have 1 over 2 times 3, or 4. 4 minus 1 minus 1 over 2 times 4 plus 1. And you'll notice that this term, if I actually carry out the calculations, will be -1/6. And if I carry the calculations here, it'll also be negative, it'll be +1/6. So these two terms cancel each other out. And you'll see the same thing applies, these, if I do the next one, if I do 5, hold on just a second. Turn my sound off here. Oh, wrong button. It's funny, I think I've told you this before, I can still hear it, even though it says the sound's off. You got to go through that thing twice to do it. Okay, so the next one would be 1 over 2 times 5 minus 1 minus 1 over 2 times 5 plus 1. So this is 1/8, and this is 1/8. So those are going to cancel each other out. And you'll keep having that happen till you get down to infinity. But in infinity, you'd have 1/2 times infinity plus 1, which is going to be 0. So ultimately, the remaining term down here is going to be 0. But all the other terms, except for the first two terms here, are going to cancel each other out. And so the answer is just 1/2 times 2 minus 1 plus 1/2 times 3 minus 1, which is, that's 1/2, and this is 1/4, so the answer is 3/4. So that's a telescoping series, and a lot of times you can figure that out because you have to have some kind of thing you can factor in the denominator, so you have two terms where one is positive, one is negative, and a lot of times you can cancel out intermediate terms. So here's another telescoping series. Now you have to let n be a fraction. Here, -3/2, and here, this is +3. No, this is +1. No, that is +1. Okay. It's like, what am I doing? Yeah, those are, one's +3 and one's +1. So that's let n equal a -1/2. So there you get 1 is equal to a times 0 plus b times 2 times -3/2 plus 1. So that's 1 is equal to, so here we have, this is -3 plus 1, so that's -2, -2b, b is equal to -1/2. That's what we got in the last problem. And then the second one, you would stick in n equals -1/2, so you'd have 1 is equal to a times 2 times -1/2 plus 3, and then plus b times 0. So you get 1 is equal to, here we have -1 plus 3, so that's 2a. So you get a is equal to 1/2. So just, I don't think it doesn't always happen exactly that way. We had two examples where that's the case, but ultimately what we end up with is this series that consists of term a, which is positive. So we get 1/2 times 2n plus 1 minus 1/2 times 2n plus 3. And you could do the same thing. You can, so why don't you guys go ahead and evaluate starting at n equals 1 in this case. Go ahead and what I would suggest is you can, previously I didn't carry out the calculations, but go ahead and do the calculations, but don't add those two together. So have the first term subtract the second term, or go ahead and simplify the first and second terms into fractions, so it's a little easier to see what you can cancel out, what you can't cancel out. And I'll do the first one for you. So this is 1/2 times 2n plus 1 minus 1/2 times 2n plus 3. So that's going to be, so it'll be 1/6 And this one will be 5, 10, 1/10. Yep. I think you'll quickly see what the pattern is. And you can see it passes the divergence test, because this, if you let n go to infinity, you'll get 1 over infinity, which is 0. So you can't just immediately say it diverges. So this is, you can, once you see the pattern, you can see the denominator is increasing by 4 each step. And this is positive, this is negative. So this cancels out with that cancels out with that cancels out with that. Keep going forever till you get, and then you'll have 0 as your infinite term. So the answer is 1/6. Okay. Okay, now we have geometric series. So we have a geometric series where the ratio, so we know it's a geometric series because we have some ratio raised to some power, and this can be either plus or minus. So ratio in this case is -1/2, and you can say since r, the absolute value of r is less than 1, the geometric series converges. Like I said, the geometric series is one of the few where you can actually figure out what the answer is. So I'm going to go back to the rule, which I don't remember everything here, so maybe in another 10 years, but I won't be here, I won't be teaching in 10 years, so I guess I'll never. Must have been here somewhere. Where's the geometric series test? All right, here we go. So the answer is the summation from n equals 0 to infinity of a times r sub n, r to the n is a over 1 minus r. Now it says r has to be between 0 and 1, but that's actually not true. It's just the absolute value. So it still works. I don't know why I wrote that down. So even though r is negative, that equation still works. So we get the answers, so it's 1 minus r, so we get a, which is 1, because this is just multiplied by 1, divided by 1 minus -1/2, so that's 1 over 3/2, because we got 1 plus 1/2, so that's 2/3. So that's the limit. And just to prove that it actually is true, we're going to make up a spreadsheet. And if you watch the homework, you'll see that I do this a lot, just to verify that it actually all this stuff is true. So I'm going to create a column which is n. I'm going to create a column which is a sub n, and then I'm going to create a column which is the sum. And we're going to start with n equals 1, I think. Is that what we started at? N equals 0. And a sub n is equal to negative 1/2 raised to the n power. So it's negative 1/2 raised to this power. So that's the first term, is 1. And the sum is equal to, is that first number. Okay, so that's the sum. And then what we'll do is we'll increment this counter, and we'll go down like 75 terms. And then I can copy this equation down. So the next one is negative 0.5. So that's negative 1/2 raised to the first power. And then the sum is going to be the new value plus the previous value. So the sum is 0.5. And once you've gotten the first two lines figured out, you can just copy the equations down. And what you'll see, this thing's alternating. And the a sub n, which is this term, it gets smaller and smaller and smaller. After 75 terms, it's down to 10 to the minus 23 power, which is pretty small. And you can see that the value of the sum is 0.6666666666, which is 2/3. So it works. Okay, so now this one is a little different because it might be a geometric series. We've got to figure out what the geometric series is. So we've got to put it in the form of where we have something a times r to the n from n equals 0 to infinity. So if we divide it, let's divide everything by 8. How about if we divide because we got to have some multiplier. So if I divide everything by 8, I'll get 1 plus 6/8 plus 9/16 plus 27/64 plus ... Is that right? I think so. Okay. I'm just thinking here. So that's 4 squared, that's 3 squared. That's 3 cubed, that's 4 cubed. This is the one that bothers me. Oh, that's 3/4. So you can reduce that down to 3/4. So this would be 3 to the first power, 3 to the second power, 3 to the third power. This is 3 to the 0 power. So it looks like we can rewrite this as the summation from n equals 0 to infinity of 8 times 3/4 raised to the n power. So you always have to start with a 1 because if you think about it, any number raised to the 0 power, if you have 1/2 raised to the 0 power, it's 1. So if you ever have a series that starts with something other than 1, you should probably divide by that number. So you start it with the number 1 and then see if you can see some pattern, which I can. You couldn't see it here, but once you divided by 8, you could. Okay, so so what we can say is since r is the absolute value of r is less than 1, the series converges. and it converges to the sum, and S is equal to A over 1 minus R. So A is 8 in this case. 1 minus R is 3/4. So you get 32. 8 divided by a quarter, or 8 times 4 is 32. And I could do this, I could plug that into my equation over here. All I have to do is change this equation, this one right here, and it'd be 3/4. 3/4. Put an 8 out front, 8 times. Do that. Copy all these things down. And you see you got 32. So that does work. Okay. How many more? Oh, I only got one more example. Then you got your homework assignment. Okay. This one, determine the convergence of the divergence of the series. It's not a geometric series, so it has. Well, the only other test we have, well, we could do a telescoping series, but the denominator is just single term, so it's not a telescoping series. And so the only other test we have is the nth term test. And so we'd say since the limit as n goes to infinity of a sub n is equal to 1/10. So we treat this like a rational function. These are both raised to the first power, so you just take the ratio of the leading coefficients. So it's equal to 1/10, which does not equal 0. The series diverges according to the nth term divergence test. Okay, so while you're finishing that, I'll give you the homework. So there's a lot there, but they're not that long, so. So we're going to kind of continue on in this vein. We introduce about 2 new tests per section for the next 3 or 4 sections, and look at examples of what kinds of series would fit into those parameters. Once we finish all the tests, we'll do a handout in class, which will look at a number of different series and try to figure out first which test applies, and then apply the test to see whether it converges or diverges. Sometimes there's more than one test that you could use. Okay, so everybody's got that. Again, I'm just going to insert this just to remind you where we're going with this whole thing, why we're doing this. The functions like e to the x are 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus ... forever. You can represent e to the x, the sine of x, the cosine of x as these infinite series. So this ends up being the summation from n equals 0 to infinity of, what is it? It's x to the n divided by n factorial. So here you have x to the 0, which is 1, divided by 1 factorial, which is, or 0 factorial, which is 1. This is x to the first power divided by 1 factorial, which is 1. This is x to the 2 power divided by 2 factorial, and so forth. So you can represent this as an infinite series, And the question is, does this converge? And you'll also notice that this has an x in it. So does this converge, and for which values of x does it converge? So that's ultimately where we're trying to get. If we have somewhat, and also how do we come up with this equation? How do I know that besides just memorizing, how did this come about? How did we figure out that this was the infinite series for e to the x? And actually, this might be a good point, just a good point to demonstrate the whole idea of infinite series and how they work. So what I'm going to do is I'm going to plot this function, and I'm going to plot e to the x, and I'm going to add additional terms. So what I'm going to plot is as the actual function e to the x. So here's what it looks like. So that's the exponential function. And what we do is we start out with the simplest representation, the equation that would predict the exponential function at x equals 0, which is right here, with the simplest function. So we start off with the simplest function would be a constant value. So we just say y equals 1. So the blue curve is exactly right at one point. It's exactly right at x equals 0. The exponential function equals 1, e to the 0 is 1, and the function y equals 1 equals 1. But everywhere else it's not very good. So then you would now try a linear approximation. So you'd add x to it. So that one's a little better. At least there's two things going on there. It looks closer as you go away from x equals 0. The approximation is better, but then it really falls apart as you get to higher and more positive and more negative numbers. The other important thing is that the slope of the blue line is the same as the slope of the red line. So not only is the function matched here, but the slope is matched. Now if I take the next term, which is x squared divided by 2 factorial, I get, this is going to be a quadratic equation, so it looks like that. So again, it's getting better. The value of the function's matched at x equals 0, the slope of the function's matched at x equals 0, and it turns out the second derivative of the functions are the same. The blue curve and the red curve both have the same second derivative. And remember, the value of the first, second, third, fourth, fifth, sixth, seventh, eighth, the value of every derivative of e to the x at x equals 0 is 1. So the 7 millionth derivative of e to the x at x equals 0 is 1. Now I'm just going to continue to add terms, and we'll see how closely we can match this thing. So I take x cubed times 3 factorial, or divided by 3 factorial. That's a cubic function. Looks even better. If I take x to the 4th power and divide that by 4 factorial, that's a 4th order equation. That's doing better, especially on the positive side. It looks, it's harder to match here on the negative side. Then I add x to the 5th divided by 5 factorial. It's a 5th order equation. Okay, I'm just going to add a couple more without stopping. X to the 6th divided by 6 factorial plus x to the 7th divided by 7 factorial plus x to the 8th divided by 8 factorial plus x to the 9th divided by 9 factorial plus x to the 10th divided by 10 factorial plus x to the 11th divided by 11 factorial plus x to the 12th divided by 12 factorial. Okay, so as I add more and more terms, the polynomial approximation here becomes closer and closer to the value of e to the x. So let me zoom out here a little bit in the x direction. Now here's the mind-blowing thing, is that this infinite series will predict e to the x correctly at any value of x if you have an infinite number of terms. It just takes a long time. I mean, you can see how far it is away from here. You can see how far the two curves are apart, the blue curve and the red curve. But if I added maybe 100 terms, I might get pretty close there. And you can see on the positive side, though, you know, we're matching pretty good for quite a distance. You'll finally start to see some separation here once I've gone up to 5,000 or whatever. But for much longer this way, well, no, actually, maybe it's not really that much longer. It's just quite a range of x value or y value. But you might think, well, this infinite series representation is only good close to zero, and everywhere it's not good. Everywhere else it's not good. But if you take an infinite number of terms out, it's going to match up everywhere. So that's pretty cool. And there's one for the sine of x, there's one for the cosine of x, which we'll look at another time. Okay, moving on to the next convergence test. And if later when we run the appropriate convergence test on this series, we'll find that this converges for any value of x. So that's how we know, not just because I said it. Not just because I said it is true, because you can prove it mathematically that it does work for every value of x. Okay, so the next two are called the integral test and the p-test. And the integral test is basically why we did section 8.8, the improper integral, because what we're going to do is we're going to rewrite the series as an integral, and we're going to do the integral, and if the integral converges, then the series converges. If the integral diverges, then the series diverges. And they're going to be integrals to infinity. The p-test is kind of like the geometric series test. It's so when you see it, it's called the p-test because p is the exponent. P doesn't change. So instead of having 3/4 to the n power, it would be n to the p power. So n becomes the base and p becomes the exponent. So it looks similar to a geometric series, but not exactly. So here's the integral test. So it says if f is positive, continuous, and decreasing for x greater than or equal to 1, and a sub n, if you can rewrite the series, the individual term of a series, a sub n, as the function, then they either both diverge or they both converge. So if we're looking for the convergence of the series, we can look at the convergence of the integral. If this converges, then this converges. If this diverges, then that diverges. So that's what that means. So they either both converge or they both diverge. So let's look at, so let's say we have this infinite series. This is summation from n equals, has to start at 1, from n equals 1 to infinity of 1 over n squared. Now, we don't know what it converges to, and this is not going to tell us what it converges to. It's going to tell us whether it converges or not. So what we would do is to answer this question. Well, first, since the limit of this as n approaches infinity is 0, we know it. We can't just say it diverges. We have to look at it. We have to do something else. So what we're going to do is we're going to look at the convergence of the integral from 1 to infinity of 1 over x squared dx. Well, we already did that problem, right? We did that in section 8. And when we had 1 over x squared, I think that converged. We won't go, well, let's go ahead and do it. You take the limit as b goes to infinity of the integral from 1 to b of 1 over x squared dx. And then you rewrite this as x to the minus 2 power. And then you integrate. So you get x to the minus 1 power over negative 1, evaluated between 1 and b. So we get the limit as b goes to infinity of, and remember this is 1 over x. So we get negative 1 over b minus negative 1 over 1. And when b goes to infinity, this goes to 0. So we end up with 1. So what we can say is since the integral from 1 to infinity of 1 over x squared dx converges, the summation from n equals 1 to infinity of 1 over n squared also converges. So that's how that works. Now if I did 1 over x, remember we did that in section 8 and that diverged. So if we had 1 over n, that would diverge because the integral of 1 over x dx from 1 to infinity diverges. Okay, so we'll stop for there. We'll see you in 25 minutes.